Welcome to AON3D. Today, we reveal Hylo, one of the largest, fastest, and smartest high-temperature 3D printers on the market. Plus, get an exclusive preview of Basis, our new additive manufacturing software and the foundation of the AON3D ecosystem. Together, smart hardware is combined with intelligent slicing and in-process monitoring, turning process variability into part confidence with just a few clicks. Without further ado, I now hand it off to AON3D VP of Sales and Marketing, Leif Teltons, to give a full introduction of Hylo and Basis.
All right, thank you, Eric. So about AON3D, for those of you less familiar with us, we manufacture material extrusion-based additive manufacturing hardware and software with a heavy focus on high-performance polymers and composites. We were founded in 2015 by a team of materials engineers, and we're headquartered in Montreal, Canada, with offices in the United States as well. We serve a few hundred customers across the globe now, and these range from small businesses to Fortune 500 companies, universities, government agencies, and industries and applications range from space, aerospace, defense, energy, automotive, rail, prosthetics, packaging equipment, semiconductor manufacturing, you name it. And what we're going to show you today is actually two new products. The first one is Hylo, our new flagship 3D printer. And the second one is Basis, our new machine learning powered software platform. So we've been developing these in parallel for the past few years to solve problems we believed were barriers to end user success or barriers to scaling various applications of additive manufacturing. So with Hylo, we wanted to deliver the largest, fastest, hottest, most versatile, reliable, repeatable, and productive hardware to date while maintaining affordability. And then we wanted to eliminate all the remaining hardware-oriented human-in-the-loop sources of error. And then lastly, we wanted this machine to be able to provide meaningful, trustworthy sources of sensor data, which ties into Basis. So with Basis, we wanted to close the feedback loop between additive manufacturing hardware and software. So create a kind of link that finally ties predictions to outcomes. We wanted to enable expert level outcomes for amateur users, right? So how do we get our new user printing parts better than our material science PhDs could have done with this, without this a year ago? And then lastly, we wanted to empower expert users with tools to increase printed part confidence. So thereby reducing downstream quality management burdens. And let's talk about the problem that we're solving. So after 6 generations of hardware and 8 years of manufacturing open material, high temperature 3D printers, what have we learned? Well, it's that high performance polymers are very difficult to print well. And there's a massive human in the loop component to that. So getting into the problem, let's look at holistic part quality first. So what you really care about is your part quality, your part performance, and your part confidence, right? You're buying the hole in the wall, not the drill. And this is very much a function of your process quality and your inputs you fed to your machine. So your hardware and its ability to process those instructions. And then you also have your feedstock quality. So if you're using good material suppliers, such as the ones we've spent a lot of time qualifying. Now, this is actually the hardest part of this whole chain once you figure out the hardware component, right? And this is where, two different users of various skill levels slicing files and telling the printer what to do, we get two different part outcomes. And, a print might actually be doomed to fail before the end user actually even hit print. The whole process was also quite linear with poor feedback loops and required qualified users at each stage to get to a maximally optimized part. And then often it required iterating back through this whole process to get there, right? Depending on the application requirements. So this is a much more powerful, much more user-friendly, and much more scalable process that we've been building. So by closing those feedback loops between the hardware and software, by building as much intelligence into the process itself as possible. This is where you enable all levels of users to get to their desired outcomes much quicker and in new ways that exceed what was possible before. So the first missing element was probably the hardest, and that was material-specific thermal intelligence within your slicer. So being able to automatically and dynamically adjust and tune process parameters based on your part geometry and based on the material that was being printed. And the other one was more advanced process control and monitoring. So providing meaningful quality data that would actually let you trust your parts more and let you know if your first print or your 100th print on your first machine or your 10th machine are all within spec. And that's where Basis and Hylo come in. And that's why these two are very much linked together as a package. And the outcome that you get is an open material ecosystem where you're getting expert level outcomes no matter your skill level. And then advanced users are also being given tools to further push the limits of additive manufacturing with respect to part performance and part confidence. So what you came here for, let's get deeper into Hylo. So Hylo is our largest printer to date with a 650 by 450 by 450 millimeter build volume. It has dual independent extruders, which are composite ready. It has all the usual print modes, including duplication mode coming in 2024. It's of course an open material system as always, and it takes pretty much every 1.75 millimeter filament on the market. Our max print speed, our travel speed, our max acceleration have all improved dramatically. And together with a completely new toolhead design, the build rate has also gone up dramatically. And together these give you a throughput of more than 8x what was achievable on the M2 Plus for most polymers. So on the thermal specification side, we now have a chamber that reaches 250 degrees Celsius, nozzle temperature of 500 C plus, bed temperature of 250 C as well. And these thermal specs combined basically give you access to every single high performance polymer currently available on the open materials market. The other interesting thing we've done is, and this took some very clever engineering on the kinematic compliance and structural loop side, but we're able to go from ambient temperature to print temperature for most engineering grade materials in less than 20 minutes. And we're able to do so without any loss of accuracy or print quality. So once again, with those thermal specs, you are able now to print very large parts in any material from ABS all the way up to carbon fiber PEEK. Once again, this is an open material system, so if it's out there on the open market, there is no license fee, no unlock fee. Everything is able to be printed on the machine in its default state. So going into more specific features, we have new on Hylo a automatic purging and wiping bay. We have automated nozzle centerline XY calibration via optical nozzle inspection, which is huge on IDEX systems if you're familiar. And we have independent Z offset calibration and actuation on each tool head. So beyond your bed being able to move up and down, each tool head is able to move up and down in the Z axis independently as well. So this gives you a very accurate automated mesh bed compensation. On the material side, we now have automatic material loading and changeover. We have filament diameter, feed rate, and tension/compression compensation as well. And we have regenerative desiccant drying for both the material bay and the feed path. So here we have a massive piece of ductwork being printed in Ultim 9085, and those print heads can use the entirety of that build area in the XY dimension as well. Given the 8x throughput improvement on this machine, plus the ability to print raftless, meaning that you print directly on the build surface without the need for a support material with every print, When you combine that with reusable build sheets and build plates, what you get is very interesting unit economics, right? You have a much quicker time to part, much lower cost per part, especially when combined with open materials. And this starts getting very interesting in terms of which applications all of a sudden make a lot of sense to 3D print that maybe didn't before. And then in terms of part confidence and starting to get into, more stringent application requirements or more demanding applications, that 25 plus integrated sensor suite we mentioned, that's going to help you do that. We're going to talk about how and basis coming up next. And what you're looking at on the right there, that is one of the included 4K chamber cameras giving you that feed, which you automatically get with every single print. All right, so moving on to Basis, our software platform. Our Basis platform serves multiple functions which fall into three categories, which are manage, optimize, and qualify. On the management front, Basis lets you manage, track, and monitor printers, projects, users, part revisions, and optimizations. And it also lets you review your as printed part data for each of those projects or iterations, right? So here we're in the project view where you can see which active projects you have going, what they look like, when they were last printed, how many iterations there were, who revised them, and as well if you took advantage of the thermal simulation and optimization tools. So here we're going to show off just how easy we've made thermal optimization within Basis. Here I have a dimensional artifact in Ultim 985. We've uploaded the geometry to Basis, which does support direct G code upload as well. But what you get by working within our slicer interface here is that all you need to do is select the material type, select if you need supports, and click Slice. Now I have my toolpath, my sliced file, and all I need to do is click Run Thermal Simulation. And that simulation would take about only 5 minutes. And here I have the thermal simulation pre-optimization, and on the right I have it post-optimization. And this is not a temperature plot, but rather it's showing areas it's identified as being likely to overheat and create visual defects or compromise mechanical performance. So how does that pre versus post optimized artifact look in practice? And here on the left, we see that the areas that were identified as overheating did indeed overheat, right? When you see that kind of drooping or sagging, it's not necessarily because of the overhang angle, but rather because that polymer had no mass around it in which to distribute heat. And without Basis, your part would have been just either manually optimized within your slicer layer by layer. Instead, what you're getting is a dynamic, transient, centimeter by centimeter optimization where you are controlling the print speed, the flow rate, everything in conjunction to get you a good looking and thermomechanically optimized part together that you see on the right. So now let's look at a larger part that had been printed and where we identified some potential defects within the Analyze module. So what we're seeing here is an actual as printed feedback from one of our sensors, which is the giving you essentially a view of inferred pressure. So that's very interesting. That's not something we've seen before, where we are able to look at our as printed data, both in terms of logged motion and the force feedback to give us inferred pressure feedback. And now we can see that there might be a problematic area within this print, right? Maybe it was a material feedstock issue where it was way over diameter and we did not have diameter flow compensation turned on. Maybe it was, if it was a smaller dot, it could have been a piece of dross or, unwanted material inclusion within the print, creating that high spot. This really gives you an interesting amount of part quality data where now if I'm looking at 100 runs of this that have been printed, and I'm seeing uncommon errors that are outside my allowables window on certain prints, all of a sudden we have a means to flag the print, take a look, inspect it manually, and either reject it or just reject it based on the pure data streaming near real time from the printers themselves. So this is huge, and this is what we've been talking about in terms of this combined with the thermal feeds, the temperature feeds, the logged position. All of this combined together gives you new high quality data streams where you can hopefully reduce your downstream quality management burdens, right? We don't like seeing witness coupons. We don't think they're a good way forward. And the way you get around that and the way you increase part confidence is not just through better process intelligence upstream, but better logging, capturing, and understanding midstream at this point in the process. So here we have an example of this feature working as intended, and ironically, it's the witness coupon which failed here. So we're printing a batch of 12 ASTM D638 tensile bars, and Basis notified us of an inferred pressure spike within a region of one of these coupons. And it turned out to be a dross inclusion, and sure enough, when we pulled it, this coupon failed at more than 2 standard deviations below the mean peak stress that we expected, right? So we were able to identify a hidden defect and be notified of it in near real time, so we could do what to decide with this print. And when we talk about tools which help reduce downstream quality management burdens, this is exactly what we're talking about, right? We also had the video feed of this print, we had all the thermal data logged, and we had one nice easy platform in which to view it all. So that's it for today. We would love it if you reached out to us with any questions, or if you want to go deeper technically on any one of the subsystems or features within either Hylo or Basis. We're happy to talk. Please reach out to us at sales@aon3d.com. And thank you once again for attending today.